from the salt part, which is given by the pressure exerted, applied by the salt water. And keep in mind that we can assume here, given that the flow is very slow, we can assume static conditions, which means that the hydrostatic law applies. We already discussed the hydrostatic law. The hydrostatic law basically allows me to compute the pressure that is exerted on this fluid particle by both fresh water and salt water. And they are the same, because otherwise I wouldn't be on the interface. This particle of fluid would move if they were not the same. So let me indicate with the symbol H, or I don't remember if in my sketch I used the same symbol, but I guess yes. With the symbol H, the difference in altitude between mean sea level and the interface, and this is what I am interested to estimate. If I want to locate the position of the interface, I need to estimate its position relatively to the mean seawater level, for instance. Okay, I know that the pressure given by this column of water, salt water, on this point, under the assumption that I have a very reduced velocity here, it can be computed in this way. P, it's equal to, let me call it gamma S, S stands for salt, times H. It is the water, the depth of the water column above the particle. You may say now, why is that? Because this water is traveling through a medium to get to the water particle, so some pressure should be spent to travel through the medium. My reply is, keep in mind, the velocity is very low. We are close to static conditions, and therefore you don't have any dissipation of energy traveling through this medium. So you can say, we can assume that the pressure that is given here is the same pressure that is given on a water particle that is placed here, because there is no dissipation of pressure through the medium. And therefore the pressure is given by gamma S times H. This is for the hydrostatic law. The hydrostatic law, I just would like to remind you, says that H, if you indicate with H the height of the water column about a given fluid particle, H plus P divided by gamma is constant. And therefore you can say that P is equal to gamma H if you select the reference level in a way that the constant is 0. Okay, so basically, let's take this relationship here and keep in mind the negative sign of pressure and the fact that, what I'm saying is I wanted to give you an explanation why there is no negative sign here. And there is no negative sign because, think about it, because it's, how can I explain it in a proper way? So let me expand this. It's H plus constant. So basically, if we measure it with respect to the sea level, we have 0 0 plus 0 is equal to constant, so constant is equal to 0. So basically, if we apply this relationship with respect to the seawater level, we have that the depth of the water column above it is 0, and the pressure is 0 at the water level, and therefore we can say that the constant is 0, and therefore we can consequently write that H is equal to minus P sub gamma, but pressure cannot be negative, so let me write it in this way. P sub gamma is equal to minus H, which means that indeed we should express H with the negative sign. And this is just to explain to you that if I measure with respect to here, H is decreasing. It's an altitude that is decreasing because I'm losing elevation, and therefore I should say that H is negative. It doesn't matter if we basically, this is just to explain why it's negative. Basically, I'm measuring elevation with respect to here. So here I have a negative elevation. Okay, is it clear? Okay, perfect. And therefore, even in this case, I should write here gamma S times minus H. But in this case, let me think about it. Yeah, because otherwise H is negative. So basically, if I measure H with a negative sign, I have to put here pressure cannot become negative. I hope it's clear. Now, let me compute at this stage the pressure exerted by the fresh water. And let me indicate with lowercase, this is H, again, and this is lowercase h. So basically the column of water above the column of fresh water above the fluid particle is given by H plus lowercase h, where lowercase h is the elevation of the water table above the sea level. Okay, and in this case I can write that this is Ps. Let me write that Pf, where F stands for fresh water, is given by the total height of the water column here, which means gamma F, because now I have to consider the weight of the fresh water, times H plus HF. Okay. Now, in order to make things consistent, I realized that I have to keep the positive sign for, I have to measure it, I have to keep the positive sign, and therefore to set H equal to 0 here. Let me think about it, because in order to compare the two, yeah. Why the sign is different? Because they are different pressure. One pressure is, let me think. Okay, let me take for now, and then we call back this discussion later, okay? Because I made a bit of confusion in taking the reference level. Let me take the pressure in absolute term, and therefore the pressure here is given by the weight of this water column, which is gamma S times H, and the pressure given by the fresh water is again given by the weight of this water column, which is gamma F times H plus H, lowercase hf. Okay, let's take it in absolute term. And then I make confusion because here it's essential, if you want to make the sign consistent, to select the reference level in a proper way. but let's discuss later about this, okay? Now let's focus on the absolute value of pressure, which is given by the weight of the water column above. And here I have two water columns pushing, one of salt water and one of fresh water, okay? So I have to equate these two pressures, and then I have to write that gamma SH is equal to gamma F H plus HF. My purpose here is to estimate H, so to locate the position of the interface. Okay? Then let me derive an explicit relationship for H, which is gamma SH minus gamma FH is equal to gamma F lowercase hf. Okay? Then I can isolate H. H is equal to gamma F lowercase hf divided by gamma S minus gamma F. So basically, I can write it in a clearer way in this way. It means that it's equal to HF, lowercase hf, gamma F minus gamma S minus gamma F. Okay, what is a typical value for gamma F? It's 1000. Okay, so basically we may write that this is more or less equal to lowercase hf, which multiplies 1000 divided by 125 minus 1000. This is a typical specific weight of salt water. When we want, it depends on the salinity, but a typical value is 1025 kilograms per cubic meters. And therefore, this is more or less equal to 40 HF. This is the relationship that I wanted to derive. Okay, and what does it mean? It means that in order to keep salt water towards the ocean, we need to have a higher elevation of fresh water inland. An higher elevation because fresh water is lighter, is weighing less than salt water. And basically, what we obtain is that if we have a higher elevation with respect to the sea level of fresh water that is equal to lowercase h, basically it means that the interface is pushed underground of a quantity of a depth with respect to the mean sea level, which is H, capital H, that is 40 times the elevation of fresh water above sea level. So if you get elevation of fresh water above sea level, you push the saltwater interface in the underground 40 times of the elevation of the fresh water. While you move inland, you get typically an higher elevation of fresh water. Higher elevation, why? Because the water table typically increases its height while moving inland. And therefore, this is why moving inland, we obtain the effect with the raising level of fresh water to push the saltwater interface back into the underground. And therefore, this is why you get a wedge shape. This is due to the increasing level of fresh water. It means that if you decrease the level of the water table because you pump, because you reduce infiltration through urbanization or whatever, you have a raise of the interface. You push back the interface if you raise the level of fresh water. Another thing that this relationship tells us is that if you don't have any over-elevation of fresh water with respect to the sea level, you have the sea entering completely into the land. If you put 0 here for lowercase h, you get 0 for uppercase h, which means that you have the fluid particle going up here to the level of the sea. So you need an over-elevation of fresh water to push back the particle in the underground. And now I still have to clarify the sign problem. It's easy, but first I wanted to just make my reasoning on the absolute values of pressure. Okay. I think this relationship clarifies what is the overall dynamics and what is our aim. Our aim is to raise the level of fresh water or do something else if we cannot do that. It also clarifies that if we dig a well here and we start taking water from it, what does it happen? It happens that you decrease the level of the water table around the well, and therefore you get a shape of the water table like this. Let's suppose that you bring the water table here, because of course if you pump inside the well, you lower the level of water into the well, and therefore it takes some time to get back to the undisturbed condition, and here you have something like that. So, what does this mean? It means that starting from here, you get something like this. So basically, you have the salt water increasing its level. Be careful, because it may happen something like this. Which means that from your well you start taking salt water. This is under the assumption that there is no mixing. Now, let me go back to the hydrostatic law, because I I want to remove the confusion that I did, without any doubt, okay? So let me go back to it. And just before I delete the blackboard, this is the figure, my figure. And basically, you may make the same reasoning with respect to a tube, which is more understandable. It's a conceptual scheme, but otherwise this is mirror, but you can see here the same figure. I think the symbols are the same, yeah. Okay. Now, hydrostatic law. Sorry for that, but I want to remove any doubt that I might have generated. I already mentioned to you the hydrostatic law, and it is written in this way. Let's suppose that you have a type of water, which is a classical example of an hydrostatic system. Hydrostatic means water that is not moving, okay? Water that is not moving, okay, perfect. So let's suppose that you have this tank with this water level, and let's suppose that we want to make reference to a generic fluid particle, and which is located, this fluid particle, if we indicate this plane as z equal to 0, this particle is located at altitude z with respect to my reference. On this fluid particle, I have a pressure acting on it, and the pressure is given by the weight of the water column above it. So the hydrostatic law says that Z plus P divided by gamma is equal to a constant. So, where it was the mistake that I did before, that changed my sign? My problem was that I made reference to the quantity H, which has a different sign with respect to Z. So this is the way to express the hydrostatic law. And you see that for increasing Z, you have decreasing pressure, which is fine, because if you take a fluid particle that is located here, this has pressure 0, and this is Z max. So basically, if I apply the hydrostatic law, I could say that my constant is Z max, because the pressure is 0. So basically it works. In this way it perfectly works. Increasing Z means decreasing pressure. Okay, that's fine. My only problem was that I made reference to H, and this is fine, but if I want to make reference to H, I have to change the sign. And I have to change the sign because increasing Z means decreasing H. So if I want to make reference to H, I should write minus H plus P divided by gamma is equal to a constant, and the constant is different, it changes, because now I'm making reference to, if I go to the level, to the surface of water, I would say that 0 plus 0 is equal to my constant, and therefore the constant is 0. In the other case, the constant was Z max. So basically, the reason why I couldn't find the right sign was that I made reference to the water depth above the fluid particle instead of the particle elevation with respect to the reference level. But what matters is that in any case you have to keep in mind this, apart from any convention, from any agreement on the reference level, you have to remind that the pressure on a fluid particle is given by the height of the water column above it divided by gamma. Okay, so basically, if you invert this, you obtain that basically P is equal to minus Z in this case, but minus because it refers not to the height of the water column, but the elevation of the fluid particle. So this will be written as minus z multiplied by gamma. If I want to write h here, I have to write p is plus constant, which becomes equivalent to p equal to h plus gamma. Because the constant is z max, and therefore if you make minus z plus z max, you obtain h. Is it clear? So just keep in mind, I won't ask you the electrostatic law at the exam. Just keep in mind that on a fluid particle the pressure is given by the height of the water column above it divided by the specific weight of water. And therefore, with reference to this case, you obtain that gamma f times HF is equal to gamma S times H, like I did before.
And in terms of weight between the saline water and the fresh water?
The weight, it's as I said, the fresh water is typically the weight is 1,000 kilograms per cubic meter. Kilograms force.
But the saline water is not a bit heavier?
Yeah, it's 1025. It's the
1025, it's like really small.
Yeah, it's small. The difference is small.
But it's enough to make the difference between the two layers.
Yes, of course. It's enough, and it's enough to motivate the fact that it's a small difference, but it's enough to motivate the fact that you need a higher elevation of fresh water to push it. Okay, and so basically this is nothing else that I've written a textual explanation of what I did, so there is nothing new, and you see that the conclusion is the same. Okay, and by the way, I think this is mistaken, and it should be inverted here. I need to correct this. Okay, it should be inverted because you see that it says basically that lowercase h is equal to 40 capital H. Instead, it's the opposite, as we just derived. Okay, and then here you have some easier explanation of what happens when you take water from a well. So basically you have an undisturbed situation where you have the well that is in equilibrium because you have a higher elevation of fresh water. If you start taking water from the well, it may happen that the salt water gets into the well, and therefore you get to the situation where you have contamination of fresh water by salt water. Okay? Now you have some discussion of the causes of infiltration of salt water in coastal aquifer, which may be, we already discussed them, which may be a raising of seawater level, change in precipitation, increased evapotranspiration. We didn't discuss this. If you have an increased evaporation for global warming, it means that you may have a lower elevation of fresh water, and then you may have saltwater intrusion. And these are the factors. We already discussed some of them. So subsidence, local climate change, urbanization, change in soil permeability due to urbanization, or increased consumption of water pumping. We already discussed them. Now, a few words on monitoring. Monitoring is essential because, to understand the dynamics of aquifers, which means groundwater, it's not so easy because it's difficult to observe these water bodies. While a river can be easily observed, a groundwater body is difficult to observe, and therefore what we need is to indeed make an effort to observe them. And in order to observe a groundwater body, the most applied solution is to use wells. They can be actual wells, meaning that they are the sources, for instance, of fresh water for water supply systems. So while you pump, we observe the water that we pump, the water flow, and also we observe the water level into the well. And also we measure salinity. Groundwater can be monitored also through piezometers. Piezometers are like small holes that are made in the ground, and from these small holes, typically we don't take water out, we just observe the water level. It is important because if we start pumping water from the underground, we need to monitor not only the correspondence of the well, but also in other places, what is the impact on groundwater level. So what we do typically is, let's suppose that we have a land here with the sea, and this is the interface, and here we have our water table. This is the water table. So let's suppose that we make a well here, and then we see that the level, the water table level, goes down to disturbed location like this. But the question may be, okay, I see the water level into the well that is decreased, but how long does it take in terms of distance to recover, to get to an undisturbed situation? And therefore the idea is, okay, let me put a pipe here, a small pipe here, and from this small pipe, which is called piezometer, I observe the groundwater level. And if I see that the groundwater level is here, then I guess that it's doing like that. I monitor the groundwater level around the well. Monitoring is extremely important because we need to be aware of the situation. We need to prevent, we need to understand in advance if the salt wedge is expanding. In the piezometer we can also measure the salinity. We take a sample of water from the piezometer and we measure the salinity because it allows us to understand if the salt wedge expanded. So, how to recover from, this is a table that I extracted from an article that is linked, it's an open source article, linked in my webpage and also discussed in my webpage. There are several options to recover, and if we understand that we need to recover the equilibrium of the system, we can act with several actions. And first, we can act on water withdrawals, because typically the main driver, the main cause of saltwater intrusion is withdrawal, groundwater withdrawal. It's not sea level rise, it's not climate change. It may be a tsunami, but it's very rare, very infrequent. What frequently happens is that we take water from the wells and water demand increases, so we take more and more water from the wells, and at a certain point we realize that the water in the well is saline, is salted, and therefore we need to go back. So, in order to go back, what we can do is to modify our water withdrawal and water deliveries. So we have to reduce pumping from the well. We may also act by injecting fresh water into the well. It is an opportunity. And then there is the possibility to act with engineered structures, and therefore we can impede the saltwater intrusion, or we can inject fresh water, as I said. And here there are a lot of references, examples of case studies and scientific papers discussing these actions. What I may ask you at the exam about this is just a discussion about possible solutions for recovery. And keep in mind that sometimes we have, and it's discussed in my webpage, we may have the options to retreat simply. So the question is recovery or retreat. Maybe that it's less expensive to retreat, which means that you may decide to close wells that are located in the proximity of the coast and retrieve the others. Okay, that's it. Okay, that's it for saltwater intrusion, and I think we can stop here for today.